Good afternoon, everybody. This is Fred Song here from University of Wisconsin-Madison. Today I'm going to present to you our CTEDD Seed Grant 2019 funded project entitled Safety Effects of Transit Signal Priority, Magnitude, and Mechanism. So this project was done in collaboration with the Minneapolis-St. Paul Metro Transit. And we studied their Route 5 bus route. This bus route runs through the city of Minneapolis and covers the metropolitan area, its adjacent cities, all in Hennepin County, Minnesota. In March 2019, Metro Transit finished implementing transit signal priority at 30 signalized intersections along this route. No bus stops were relocated, but there was a bike lane and crosswalk improvement project implemented during that time in the north section of this bus route. So the distribution of the 30 signalized intersections are as shown on this route map here. So the north section had 18 signalized intersections with TSP implemented, and the south section had 12 signalized intersections with TSP implemented. The technology implemented on Route 5 was Amtrak GPS-based TSP. So the work mechanism of this GPS-based TSP is that the system, which was installed in all the Route 5 buses, collects the information of bus locations in real time. That data updates every 8 seconds. And when a bus is approaching a signalized intersection with TSP implemented, the system on the bus will record the GPS location and knows where the bus is. If the bus is approaching the intersection, and if the bus is delayed, it will send out a request to the Amtrak priority detector, which is installed in the signal controller. And the signal controller will determine whether to grant a TSP or not, depending on the bus's schedule adherence and the location and speed of the bus. So the TSP detection and request procedure has 3 steps. The first one is a pre-check. The pre-check zone was usually set up 2 blocks away from a signalized intersection. And in this step, the bus's schedule adherence and location information were collected. And then, the TSP request was not sent out. When the bus moves to the check-in zone, which is usually 1 block upstream of the signalized intersection, the bus will send out a TSP request, and the controller with Amtrak system installed will determine whether to grant TSP to the bus. And once a TSP is granted, the signal will adjust the time, and it gives the bus either early green or an extended green to let the bus clear the intersection. And right after the bus clears the intersection, it will enter a checkout zone and let the signal controller know that the bus has already cleared the intersection, and the TSP can stop, and the signal controller can start recovery, the recovery process from the TSP signal timing adjustment. So as we know, the TSP was installed primarily with the purpose to improve bus operational performance, to reduce delays and travel time between stops. But since TSP changes signal timing, we don't know whether it affects safety or not. Signal timing is usually considered to be linked directly to traffic movements, so it may have some safety impacts. So from a literature review of previous studies, we did find that TSP affects safety in general. So there have been several studies conducted in Canada, Australia, and recently by our group in the United States. We selected the TSP implementations in Seattle and Portland to do before and after or time series analysis. And most of these previous studies reported a reduction in number of crashes after TSP was implemented. But some of the early Canadian studies reported increase in number of crashes. But they used a very different method as the other studies. They used a cross-sectional study just to look at whether the intersection has TSP or not, and compare those safety performance of signalized intersections. If they had TSP, they found that their crash numbers were usually higher than those signalized intersections without TSP. So all of these previous studies were aggregated level safety analysis using crash number as a measure of traffic safety. But we know that after TSP was implemented, that there might be some changes to crash numbers, but the mechanism of TSP affecting safety is still not clear. So with this collaboration opportunity with Metro Transit, we could get very detailed data of bus movements around signalized intersections along their bus route 5. So we could carry out a more in-depth study to find out what's the role of TSP in this process, in this TSP request granting process in affecting safety performances of the intersection and of the route. So our objective of this study was to find out change in bus-involved crashes and also in vehicle passenger incidents. Since buses receiving TSP, there may be some changes in bus movements. So we consider that in vehicle passenger incidents were also to some extent related to changes in bus movement, possibly affected by signal timing adjustments. And we also carried out surrogate safety analysis to find out effects on bus movement, which was directly related to crash and incident risks, as we assumed, by the TSP implementation. So we obtained data from Metro Transit from April to June, the 3 months from 2018, which was the before period when no TSP was implemented on bus route 5, and the same 3 months from 2019 when TSP was implemented and was activated along bus route 5. So by collecting data from the same period of time from the before and after the TSP implementation period, we can make sure that some factors are controlled, such as weather. Since Minneapolis and St. Paul was in the northern part of the United States, in wintertime, they usually get very severe snowstorms. So that could affect safety performance of buses dramatically. But during springtime from April and June, we should be okay without the effect of snowstorms, which were very uncertain and may affect our analysis results. So we got these data as we listed in these bullet points: bus route information, schedules, intersection geometric features along the bus routes, and bus crash and passenger incident records. They keep a very good archive of bus crashes and in-vehicle passenger incidents records in Metro Transit. And of course, we have automated vehicle location records from the buses for the before and after periods. And we also got TSP request records from April to June 2019, after the TSP was implemented along bus route 5. And these were downloaded from the Amtrak equipment installed on the buses. And we also got weather records from the National Atmospheric Data Center database from the before and after period. So the first part of our study is a simple observation of changes in bus crashes and passenger incidents. We found that overall, the bus crashes and passenger incidents reduced 16%. There were 44 crashes and incidents in 2018, the before period, and 37 in the after period of 2019. And then we looked at only bus-involved crashes. It reduced also 16% from 19 to 16. And in-vehicle passenger incidents also reduced 16% from 25 to 21. Then we took a deeper look into the types of crashes and passenger incidents that were considered directly related to traffic signal and possibly TSP. We included these types, these 5 types here. One type of crash is vehicle hit bus crash. And 4 types of in-vehicle passenger incidents, usually passenger fall over incidents related to bus movements, starting, stopping, turning, and when it's running straight. And we found that you can look at this chart here. These types of crashes and incidents all reduced in the after period compared with the before period. Overall, these 5 types of crashes and incidents reduced 69% from 16 to 5. So this is a simple observation, and these results are consistent with what they found in previous studies of general TSP effects on number of crashes. And then we have the AVL data. We were thinking about, well, we can use the AVL data. These are very detailed data that reflects bus movements. And we were able to carry out an event level analysis. So an event is defined as a bus approaches and clears a signalized intersection in our study. So considering that on Route 5 each day there are over 70 of these events happening because buses moves upstream, upstream and downstream of the bus routes, and they approaches and clears intersections all the time. So there were over 70 of these events happening on each bus operating direction. That's for one intersection. So for both operating directions of the bus route and of the 30 TSP intersections on bus route 5, there could be over 4,000 and 1,200 events happening each day. So we were able to get a lot of data from the AVL data set to look at bus movement when they are approaching and clearing the intersections. And here's our assumptions for our study. We assume that bus crashes and passenger incidents are closely linked to bus movements. These, I think, pretty easy to understand. And bus movement may be affected by traffic signal timing adjustments or from TSP, which initiates signal timing adjustments.
Yes.
And using these AVL data, we can get information of moving speeds and trajectories, which reflect the operating status of the buses. So a surrogate measure is defined as measurable variables describing initial conditions and road user actions, risks leading to safety outcomes, of course, crashes and in-vehicle passenger incidents.
Apartment 1105.
So in this study, we calculate a measure of bus movement, which describes the movement of buses when they are clearing the intersection. It's calculated as a coefficient of variation of interval speeds, since we have AVL data with equal intervals every 8 seconds of GPS locations and bus directions and all sorts of those variables. So we can calculate using the location data and timestamps
JPW
of a bus movement.
X4.
So this is what we used as a surrogate safety in our study. And then we have to process the data. Since we have AVL data from all of those 6 months, 3 months from the before period, 3 months from the after period, we need to extract the data and only use the data that are from around the 30 signalized intersections with TSP to do our analysis. So we set up limits based on the TSP zones. We only use the check-in zones as our both from northbound and southbound of the bus route to set up our limits for AVL data extraction. So as is shown on the figure here.
I guess it's Blue Cross Blue Shield.
Then after we extract all the AVL
that.
data, we could calculate bus movement roughness for each.
No, it's PPO.
So what we use to determine one event of one bus going through one intersection is a unique ID, which was a combination of bus ID, date, and its trip ID. One combination of bus ID, date, trip ID form unique ID for an event. And the calculated roughness score, if the score is higher, it means more sudden decelerations or accelerations in the bus movement when the bus is approaching and curving.
A few weeks ago, I did go see a GP. I'm not used to the PPO
so
model.
This chart shows the data processing
I went to the GP
procedure. We obtained these 5 raw data sets, and then we combined them
and a few things, but,
calculated the roughness scores.
There was a minor pain reliever, but
and
that's as far
formed
as
the event level data set.
Speaking to a professional about it, but
at each intersection, and then we
combined
the event level data
so it's something
together with the TSP request data.
I appreciate opening.
We use the event level. We use the intersection ID, operating direction, date, and bus ID to combine the event level data and requests. And all the extreme values in bus movement roughness and approach speed were excluded. So there could be some errors or noises in raw data. So
the best they gave was
in those cases there might be some extreme values,
but nothing
generated from our calculation.
Yeah, they were a DO. They had a bunch of
so the final data set
not working.
Consisted of 23,123 rows of events and 23 variables for all 30 studied intersections for both the before and after periods.
Yeah. Okay.
Sorry, there's some problem with my PowerPoint here.
A little bit.
Let me open it again.
Okay. Arlington. Yeah. Okay.
Okay. So after combining all the data, we got the final data set, and it had 23 variables, which are listed here, including the outcome variable of bus movement roughness, and some variables reflecting bus operation status, including the TSP request, and also weather variables, including temperature, precipitation, humid, visibility, and wind speed. Roadway and intersection information, one-way street, whether it's a near-side bus stop, number of lanes and turn lanes, whether it has a curb extension or called bulb out, intersection approach, whether it has street side parking, or a bike lane on the right or left-hand side, and also curb cuts. And we also had 3 indicators of high incident intersections. These 3 intersections had the highest number of bus-related crashes and in-vehicle passenger incidents from the before period. So we would like to look specifically at these 3 intersections, whether they are different from other intersections in terms of safety performance after TSP was implemented. So in our analysis, we used
Okay, thank you very much.
linear regression to look at the effects of TSP on bus movement roughness. And we also used tree-based models to
All right, thank you very much.
look at TSP's interrelationship with the other variables, the other independent variables that are affecting the dependent variable of bus movement roughness at the same time. We also used the random forest to compare the importance of variables in the tree-based model. So I'm not going to get into details of these methods here, so we can jump right into our results. So from the linear regression model, we can see that TSP request did have a significant effect on bus movement roughness. So as we mentioned before, if the roughness score is higher, it means not desirable situation where buses have more dramatic decelerations or accelerations during the movements through the intersections. And the TSP, we found that when TSP is requested on round 5 for an event, bus movement roughness reduces by 0.04. But at the same time, we can see a lot of the other variables are significant factors that are affecting bus movement roughness. So by including these variables, we were able to have a better estimation of the actual TSP request effect on bus movement roughness. So it's worthy to take a look at the other variables too. We can see that the before and after period bus movement roughness was not very different. So there was not a very significant change in the overall bus movement roughness. But when you have a TSP requested, bus movement roughness generally reduces. And we also found that the intersection geometric factors such as one-way or near-side bus stops are all significant, and they had higher higher coefficient absolute values than the TSP request variable here. So the bus movement roughness ranged from a minimum of 0 to a maximum of 2.69 with a mean of 0.9 and a standard deviation of 0.57. And 8% of our events, both from both the before and after period, had a TSP request. So here's a distribution of our outcome variable here. And from the tree-based models, unfortunately, we were not able to see TSP request in the regression tree that we got here. That's because TSP comparing with the other variables did not have a very large effect on bus movement roughness. And we can get that, we can be confirmed from the random forest results here of a comparison of variable importance. We can see that TSP requests comparing with the other variables, such as approaching speeds of buses and near side bus stops, or turn lanes and bulb outs. The effect of it was not as large as the other variables, but it did have had significant effects on bus movement roughness. So finally, a summary of our results and findings. Our observation of the before-after changes found that crashes, bus-related crashes, and in-vehicle passenger incidents did reduce after TSP was implemented on Route 5. This finding was consistent with most previous studies. And with an event level analysis, we were able to find out TSP's effect on bus movement roughness, which was considered as a surrogate safety measure that was considered directly related to dramatic movements of buses, and dramatic movements of buses were considered directly related to risks of bus-related crashes and in-vehicle passenger incidents. We found that bus movement roughness reduced when TSP was requested. So TSP could help buses to clear the intersection without dramatic stops or accelerations, which helps the buses to move through the intersection smoothly without encountering a higher risk of getting into a crash or have more in-vehicle passenger fallovers and incidents like that. Also, from the tree-based models, both the tree-based models and the linear regression model, we found that other bus operational characteristics, such as the bus approaching speed and delay, as we saw from the previous slides, and also intersection geometric features, such as near-side bus stop and curb extension or bulb out. These variables also affect bus movement roughness, showing their importance in these models. So our recommendation is, when implementing TSP, its safety effects should be evaluated. And we did find the safety effects from TSP. But the safety effects of TSP should be evaluated together with changes in bus operational and intersection geometric factors. This is our recommendation for consideration of transit agencies for their future implementation of TSP, if they want to consider safety in their TSP evaluation in their design and planning process. So thank you. This is our project, and it was funded by CTEDD seed grant from 2019. We are very grateful for CTEDD to fund us for this analysis. We hope we can be a part of CTEDD for a long time in the future, and get more projects done with the help of CTEDD. Thank you very much.